So thank you to everyone who has come to our industry representatives, Max and James, and to everyone else who has come. Thank you so much for taking your Sunday to be here. So I'm Drew. This is Katie. We're the two co-leads of the satellites team of SSI. All right, let's begin. So we'd like to do some introductions of both the members of our team who are here and those who aren't part of the team. So let's just go around in a circle and do introductions. I'm Drew.
I'm Damien.
I'm Alex.
I'm Tim.
And please do say your company affiliation or SSI team as well. Yeah.
My name is James Spicer. I'm chief engineer at Odyssey. I was in your shoes a very short time ago. I'm excited to be here and see what you're up to.
I'm Max. I'm an aerospace engineer at Maiden Space here at the NASA Ames Research Center.
My name is Orion. I used to work on the satellite square mission.
I'm Julia. I'm on satellite. I'm Shai. I'm a satellite avionics lead.
I'm Connor. I'm the lead of the structures and the dressers teams.
I'm Roman. I work on the software team and also the structures team.
I'm Natalie. I'm the satellite software lead.
And I'm Katie.
All right, let's move on. So the goals of this presentation are to demonstrate what we have, the progress we've made so far on our two projects, and lay out the what we plan to do, our designs for the future, and then get some critical feedback from those who are here on our designs. So first we're going to talk about the team as a whole, and then we'll go into our two projects currently labeled QuickSat and LongSat, or our long-term project. So first for the team.
So SSI as a whole has over 200 members. We're one of the biggest clubs on campus. So right now we're with the satellites team, obviously. We also have our rockets, balloons, operations, bio, policy, etc. Teams that do a diverse number of things in the space industry. So the goal of our club is to inspire love of engineering and space on Stanford's campus.
So in terms of the history of the satellites team specifically, this was our last project, Pointer. It was a payload on Odyssey 0, the CubeSat recently launched by Odyssey. It was very kind of them to lend us space on their CubeSat. Pointer was designed to demonstrate bidirectional communication optically between a satellite and the ground. And it utilized some really interesting movable mirror technology that we're really proud of. It launched with Odyssey 0 in November on a SpaceX Falcon 9 on the spaceflight SSO-A mission. So what we achieved from this project was we developed this optical communications capability that we aim to demonstrate. And we completed and launched our first CubeSat payload with this project. So some issues that we encountered were mostly during launch. Because of the nature of the launch with spaceflight, no contact was achieved between the ground and the satellite. This was due to the fact that dozens of satellites were released from the spaceflight payload adapter at the same time, making it very hard to determine which satellites were which. And James can correct me on this if any of this is wrong. So we learned from that we definitely want to be careful when developing our technology and when acquiring launch to make sure something like this does not happen. and that very kind companies and other resources exist out there who are willing to help us out and are resources that we can definitely use. So now on to QuickSat and our motivations for this project and what we hope to accomplish.
So our motivation for this project was to have a project that we can complete within a year that students can work on and have something tangible experience-wise for space. So this will be the first standalone project that SSI will ultimately put into orbit is the goal. So a lot of us don't have experience in developing satellites. We have a lot of freshmen on our team, so we wanted to be able to develop this satellite and launch it to give people that experience and ingrain a love of space. So this is a calendar of what we want our project timeline to look like. As you see, it's just 1 year long, so we're trying to do this in a short timeline. So right now we're in winter quarter, we have our first design review. In spring quarter, we're going to dive more into product development, really get into the technical details, and have a progress review at the end, probably internally in SSI. And over the summer, a lot of our members are staying in the Bay Area and can work on this project. So in August, we're applying for a ride with NASA that gives free educational rides. And in fall quarter, we'll finish up development, and we aim to have in December a full assembly completed.
Thank you for coming. I see you just arrived. We just started with some overview of SSI and the project. So for QuickSat, we have sort of 6 objectives technically that we're trying to accomplish. So we'll lay those out now.
The first objective is orbit determination without GPS. So the motivation behind that is that currently military and commercial satellites rely on GPS if they have to do location, but many times GPS can cut out and then they don't have communication with ground or know where they are in the world. So our system, we use images to determine where the satellite is and replace GPS.
So we're also aiming to have a high power radio on the satellite. Currently, the state of high power radio on CubeSats is 1 watt power is sort of a very high power for radio, but this would allow about half a megabyte per second of downlink, which means roughly 60 large images in 1 5-minute pass over a ground station. For this satellite, we would really like to improve upon that. To send more images down at lower altitude, or for our future satellites to be able to communicate with Earth effectively in higher orbits. And this plays quite well with our next objective.
Our third objective is to do Earth image classification. So given a set of images, we want to know what images to downlink. So currently when satellites go over a ground station, they can only downlink a certain number of images given how long they're over that ground station. So when you send down images, you don't want to send down images of clouds or something that's uninteresting. So we want to be able to identify what images are interesting and only downlink those. So another software objective that we have is star tracking. So in our QuickSat mission, that will be used to determine our altitude and just do general navigation things. But long term, we want to have a mission that could potentially go to deep space or something like that. So star tracking would be helpful in navigation for those terms. We also have a SIMS team. So SIMS is working on developing an overall SIMS testing platform. So currently in SSI, we have a variety of different projects from rockets to satellites to other teams that need simulations testing. And right now, all of those teams do individual development for simulations. So if we could create that in an overall modular platform, that'd be helpful for all of SSI. So we're going to start by making that for satellites specifically and for this QuickSat mission. So right now, we want to take the data from this QuickSat mission, use it to test whether our simulation software actually works.
And then another objective of the QuickSat project is to demonstrate a foldable solar array technology. The motivation for this is that we really need more power. And that's for the high power radio, as well as planning to run neural nets on the satellite. And then for our long-term project, an electric thruster will need more power than sort of one side of the satellite full of solar panels would be able to provide. Plus, this is an interesting mechanical and electrical challenge. So the sub-teams of satellites that will be involved in QuickSat are software, avionics, and structures, sort of doing all of those objectives that we laid out before. So now we'd like to discuss sort of what each of these sub-teams will be contributing to the project. So for software, I'll hand it over to Natalie.
Okay, so I'm Natalie, and I'll be presenting on behalf of the software team and the different sub-projects that we'll be working on for the QuickSat project. Our three main projects that we're working on, first of all, is star tracking. So we'll be building a star tracker system. We'll be working on image classification, back to one of the missions or objectives we were looking at earlier, where we want to decide which images are interesting, which ones are worthy of precious downlink time. And finally, we want to focus on feature matching and performing our own geolocation based on our satellite images. So first off with star tracking, this has kind of been one of the first things we've experimented with this quarter, given that this is something that can be used on lots of different CubeSat systems. So this quarter, we've built parts of a prototype star tracker, and the inspiration for that was a search tree algorithm published by the Nanyang Technological University of Singapore. So we kind of have a flow chart here of the different processes. Oh, it doesn't work on the screen. Oh well. So given our images of the stars from our satellite, we first have some image pre-processing that's involved before we actually want to run our algorithms to determine which stars are in the image. So we've written some sun shading algorithms in Python, and our actual star search algorithm is written in C++ right now. Behind our search tree algorithm, we have a star catalog, which was formed from the European Space Agency Gaia archive, which it's just this massive database of stars. We had a team member who was very knowledgeable on this that helped us whittle it down a little bit to the stars that we think would be appropriate to be seen by a CubeSat. However, we will further refine this, which leads us to our next steps for our star tracking work. We want to refine some of our image processing algorithms, so the centroiding, we just want to make sure that's entirely accurate. We also want to work on filtering. Those are two important image pre-processing components of this. And we also want to test our star tracker. There's a lab on campus that we will probably have access to test this in. And from that, we also want to refine the algorithm that we're using. Our next project for software is image classification. So back to one of our objectives of not wanting to waste downlink time on images that are completely occluded by clouds or maybe just pictures of the open ocean. We kind of want to have a choice in what images we look at, and we want to be selective with which ones are sent. So one of the first objectives of this is to simply discard images that are completely occluded by clouds, because that's not going to give us much information, which later on will be a lot more helpful when we're trying to locate ourselves also, because if our pictures don't have any geographical information on them, there's no way for us to really tell where we are in the world from that. But beyond that, we also want to categorize images by geological features. So some examples of things we could classify for would be rainforests, deserts, coasts, the Arctic, and other large macro features like that. So because this is a classification problem, we're looking at using neural networks to see what's in the image. And since this is a classification problem and we're building neural networks for this, we'll have some training data and labeling. So right now we've already looked into getting a data set for this and the software that we'll be using to label it. Our data set is the Landsat 8 imagery, which we source from the US Geological Survey. Again, it's just a massive data set that we can use for this project. It contains a lot of variety of images, kind of like some of the sample ones pictured on the left. There's also, for actually labeling everything, we're looking into using the label box software, which will help us with labeling images and also segmenting different things in the picture. So maybe we just want to see, identify that all of these little things right there are clouds and not the entire image. So labeled box will allow us to do all of those things. And our last project, and potentially our largest one, is the idea of orbit determination without GPS and just like geolocating ourselves based on our satellite imagery. The biggest question on this is how we perform this feature matching technique to the globe. So if we have a picture taken from our satellite, we want to be able to match those features to a larger image of the globe, which is a pretty big image matching problem. So I think our biggest project goal right now is looking into how we could potentially do that with software. And additionally, we want to look into how we can verify our geolocation in the end, because it's one thing for us to attempt to do this, but we also need some form to validate it. So we're thinking of either incorporating an onboard GPS or simply sending down our geolocated images and comparing that with the expected versus actual values for them. A little bit more about our feature matching and geolocation. The biggest thing that our team is looking into right now, which involves talking with some professors and seeing which direction we should go in, is just researching pattern matching algorithms that will allow us to identify a very specific place on the globe. Right now, our kind of thought process of how this could potentially work is we capture raw satellite images and we try to match that to the globe. And if we can't match it with a high enough confidence level, we can kind of just capture more images and stitch them together to where we have a larger image or a larger piece of the puzzle to look at. And that we can try to match again until a specific confidence threshold is met. Once that's met, we can assert with a certain level of confidence that we've identified where we are in the globe. And with that, we can use this information for our future attempts to geolocate ourselves by just limiting our search space. So again, the biggest thing that we need to look at is which algorithms we want to use for this and what direction we want to take. So that's it for software. I'm going to hand it over to Shai, who will talk about avionics now.
Thanks. Cool. So I'm Shai. I'm the avionics lead. Just going to get into it. Yeah, I figured out the word thing. Exciting. So as a quick overview, we're just going to go over what type of electronics will be on the system. We're going to talk about sensors, flight computers, solar panels, magnetworkers, which are functioning as like our ADCS, and finishing off the radio. So sensors, textful, I'm so sorry. But we have three main sensors we're hoping to implement. First is an IMU for obvious reasons. If we're tumbling, we want to figure out why we're tumbling, how we're tumbling, so we can do something about that. Temperature sensors to make sure we don't die, and image sensors because we want to kind of build our own camera for software to use for all the beautiful pictures they want to take and put back down. We figure we can probably do this. We can optimize it the best in-house. Plus, it's an interesting project to do. So we're hoping that all of these will be finished roughly by the end of this quarter, potentially into early next quarter. Similar design considerations amongst all of them. We want to make sure that it's like very low noise, low package, low power draw, and low price, because let's be honest, we're college students. If you want to look at the specs, we can talk more about those in the breakout meeting. I don't want to like ruin your time with just like low. It's pretty good, reasonable accuracies. We're optimizing for that. So that's kind of that's where we're at right now. And like with a large, particularly with the image sensors, we have a large array of resolution sizes and rate, like frame rate, which we're going for. We're hoping to potentially have 2 image sensors on the satellite to kind of optimize for the resolution and for the frame rate to make sure we can do image, like have fast image tracking in the future with a high frame rate camera, and have a high resolution one again to take those great pictures that QuickSat needs. Anyway, guess I covered that all. We figured we settled on the Raspberry Pi 3 Model B Plus for our flight computer, primarily because we have a lot of experience with it on the team because it's used in a number of classes on campus. But we've also looked into Beagle and Black, FPGAs and Jetsons, but realized that they were either like just needlessly like overpowered and just complicated to to use compared again to the Raspberry Pi, or again just have a lot of power and large package sizes. Has pretty awesome specs. Hopefully you're all familiar with Raspberry Pi, and again it's low cost and has a large user base. So if we run into these problems, it'll be hopefully easy to debug. We're also hoping to make solar panels in-house. We're starting to start conversations with SolarCar about how to go about this, and I've been looking to a lot of papers recently on solar panel design because it is very complex. But we're hoping to go from if you're familiar with solar panel design, we're hoping to go from the wafer versus actually worrying about how the silicon's going to get there, which will hopefully help significantly decrease the costs, because right now the solar panels go for many thousands of dollars, depending on to tens of thousands of dollars, depending on how much you want for the deployable satellites. So we figured doing it in-house is probably the best alternative. We've been looking into a few different types of bases for the solar panels. Silicon is obviously the most popular semiconductor out there. So we've been looking into that, lots of resources, and it's just very common. Also, a lot of papers have been indicating that gallium arsenide might be a viable alternative, just because it has really high band gap material that'll allow for there to be really good electron flow, and has high temperature coefficients, high low light performance, just way more efficient, twice as efficient as a silicon-based solar panel. It's a matter of it's slightly more expensive, and also there's a lot less resources on how to go from step A to final steps. So the feasibility might be a question that we're looking at right now. We're also looking at copper, but not really realistically, because it's pretty low power output, but there's infinite resources about that, because you can do that in a kitchen. Probably not space grade in a kitchen, but the same idea. And we're also developing magnet workers to again help us with detumbling. If we realize we're off orbit or doing anything weird, we want to be able to do something about that. And a 1U we're kind of space constrained, so we can't really do a flywheel effectively. So we've been looking into magnet workers. Particularly, we've been looking into two main ways of doing magnet worker. First one, that's the most realistic one, is probably our PCB spiral. So you just kind of have traces of PCBs that work within a PCB to kind of work as an inductor almost, and use a magnetic field to hopefully be able to detumble and form a dipole with the Earth. And if you have enough traces, enough parasitic condenses right there, you'll be okay, hopefully. So we are trying to figure out the math on this right now. We have some people working on developing this PCB, and we'll test it in-house, hopefully see if we get those results we're hoping. But the drawback is that it's not the most powerful way to move a satellite. So we've also been looking into a metal core magnet worker, which will be a physically larger size, which is unfortunate. And also leaves a lot of magnetic residue to be controlled, as said on the slide. But it means it's easier to physically do. You'll have a lot higher output with it. And we also already have all the wire, all the material, the solid core. That's for the magnet worker, for the metal core. So it'd be pretty easy to do in-house. We currently have some people working on making a winder for it to be as precise as possible, because I don't know how much you can wind a wire 1,000 times, make sure you're at exactly 1,000 at the end. So we're going to try to make a machine to do that. And we're trying to, at the end, we'll kind of weigh how effective it is, given the size constraints, and reliability of the two. So that we're currently experimenting with both of those right now. Lastly, we have our radio we're developing, which I'll hand off to Damien because he knows it best.
Hey everyone, I'm Damien. So the Tpmt radio, or just the radio in general, is going to be completely developed in-house. I've been working with Dr. Manchester with his CubeSat projects, and what we found is we've been trying to find higher power radios, in the 4 to 5 to maybe even 10 watt range, and most commercial offerings are in the 1 to 2 watt range. So we wanted to kind of see if we could develop something in-house that would give us the higher power, and therefore we could get the higher data rate for this sort of project to get more data through in each pass. So this is what I've kind of been focusing my work on. The kind of concept we're going through right now is a CC430 based radio, which is a TI MSP 430, if you're familiar with that, based module with an RF core, good up to 1 gigahertz. So we can do either the 430 band or the 915 band, depending on which we can get licensing for. I've been doing part searches to see what's available, like in individual like components. I found that there's not really like front end modules for this high of power, so you kind of have to spec each part out individually. And I've been working to get a prototype out of that within these next probably few weeks. Yeah. So the other option, if you didn't want a higher power radius, to do like a phased array, that involves a little more research. So yeah, so my power target is for this first one is 4 watts. That's double the power of another of the radio I'm kind of basing this off. If you know OpenLST, the Planet Labs one, I would kind of looked at that design and based this as like my reference. So I looked at that, how it was built, like kind of which parts they picked, and then from there kind of evolved that to fit our needs. So if you have any questions, please talk to me after. Yeah, so I think this is all for avionics. We're going to pass it over to Connor and Roman from structures. Yeah.
Right. So, as we've probably covered before, oh wait, that's the wrong direction. Structures basically has 2 main objectives, or 2 main things that we need to make. Obviously, we need to make ourselves a frame that will hold everything together. And then we also decide that we want to make deployable solar cells. And so basically the big thing that structures has to do is make sure that nothing breaks when it goes to launch, just because there's a lot of different forces that come into play during a launch. And so some of the most important ones are just constant acceleration from the rocket. That generally should not be too significant a problem. Really what's going to kill you is going to be the vibration loads, which you'll be seeing. And so generally those have been qualified by acceleration spectral density diagrams like these here. And NASA, I believe, has like a qualification one that we can examine and make sure with our simulations that our CubeSat frame can actually survive that amount of vibration. Additionally, during stage separation, there's an additional load of shock that we have to make sure we can survive. And then finally, there's going to be for us. This time, however, we don't necessarily have that. And so our only ways that heat enters and exits the system is via radiation. And so we need to ensure that we don't overheat. And so that will be another important thing to consider. And so these are just some generic numbers that we've looked up based on the NASA qualification spectrum or NASA qualification stuff. If you want to talk more about like actual numbers, we can talk about that afterwards. So in general, the things that we need to do are obviously withstand the launch. As we've said, we need to be able to mount all subsystems. Additionally, if we have cameras and other optical hardware, that needs to be mounted with high precision elements that like won't change size or deform at all or change under heat. And then we also need to manage our thermals. And ideally, we can make this all under 100 grams, just based on what we've seen from other people. So in general, our plan is to kind of go based off of open source designs like the ones that we can see in Dr. Manchester's class, and kind of adapt those to our purpose because they've probably done more structural engineering than we have. And so we can look at those and get designs and kind of adjust that. From a material perspective, we're hoping to build this out of aluminum 7075. Aluminum is generally fairly easy to work with, while also having an excellent weight to strength or strength to weight ratio. 7075 in particular is ideal because it has a much higher yield strength than the more common 6061 alloy. The only thing that's unclear is it may be beneficial to have some sort of coating for thermals, which will either allow us to radiate more energy off of our satellite out of that, or prevent the frame from absorbing the heat in the first place. All right, and so basically the most important thing that we do for structures is to make sure that we can qualify how well our frame will be able to survive launch, and we intend to do this primarily through FEA. So some of the most important tests which we're considering conducting are frequency analysis to make sure that all of our resonance modes are outside of the range that we're anticipating to see from the rocket. And additionally, we can run linear dynamic simulations, and that will be taking in the acceleration spectral density as an input, and that will make sure that the forces are not getting out of hand. And additionally, there will be the static, just to make sure that the 10 Gs of acceleration doesn't cause any significant issues, although once again, the static part of this is probably not tremendously important. The last simulation that we have to run is going to be the thermal simulation. And so that is to ensure that we can offboard heat as fast as we are receiving it, and just to make sure that our temperature equilibrium stays within a manageable range. Additionally, beyond FEA, we're hoping that we can do some actual physical testing. So including, we can attempt to thermal cycle it by like putting an oven and then a freezer, I guess, or whatever we decide that the appropriate temperature range is. And just make sure that we don't see significant fatigue in our materials. And then we don't have any specific plans for how we might be able to like vibrate it in any adequate manner, but it would be ideal if we could come up with one to do some physical testing to confirm that our simulations are correct.
Cool. So we're also, apart from the frame, going to build our own deployable solar panels. And as we discussed before, that's more of a proof of concept for future missions than particularly important for this QuickSat mission. So of course, we have to survive launch. So figuring out how to test that, also using potential FEA or just physically testing the assembly. We're going to design a simple release mechanism. So we want as few moving parts as possible because moving parts break. Another idea that we're looking at is to make these solar panels fail-safe. So because our mission will probably not require, may not require all the power that these deployable solar panels will provide, it'd be nice to make it such so that our primary missions, so all the other missions, image classification or determination and the radio can still work even if there's some mechanical problem or electrical problem with the solar panels. Then we'll have to do a lot of testing with thermal fatigue, expansion, contraction, which kind of limits the life of many solar panels, and aiming for a power output of around 6.5 watts. So our plan going forward is to do more of a literature review, see what's been done before and what we can use, potentially find open source designs that we can pull from and scrap together our own design from. And then figure out what release mechanism we'll have and how we'll passively deploy these panels with as few moving parts as possible. And then the development of the panels themselves will be an avionics job, which Shai has discussed previously. Cool. So now we'll move from talking about QuickSat to the long-term project.
So we'd like to outline what our long-term project or possible plan for a long-term project is currently.
So the reasons for doing a long-term mission are a couple of points. First, increase technical difficulty. We have some senior members on our team who have launched satellites before, have more technical experience. They want to be challenged in what they're doing on the team. So if we give them projects to work on more long-term, they'll be able to take a deep dive into that. We also want to be on the cutting edge of the satellites industry. Our QuickSat project right now, some of it has already been done before and we're using it more as a learning project. But for our long-term project, we want to do something that's brand new and that could actually be applied to industry. Some of the tech applications we want to do are a thruster. Right now we're working on a cold gas thruster, which we'll talk about in a little bit, a long-range radio for avionics, and a interesting structures project, which is to be determined. Our goal is to launch within the next 4 years so that the freshmen on the team can see this project launch by the time that they graduate. And ultimately, we just want to get people excited about satellites and what can really be done with these applications.
So while we do have these goals for technology that we plan to develop, we don't really have an overall mission plan that is completely comprehensive yet. We've thought about raising our orbit and maybe deorbiting the satellite as a demonstration, but we haven't fully hashed out a complete plan, and that's sort of something that we would like to figure out. So first we're going to talk about the thrusters component of this project.
Okay, so first off, we just tried to set ourselves out some guidelines in terms of like, what are we actually trying to accomplish with this thruster? So the first question is like, is there any amount of thrust we need? And the answer is not really any specific number, just because there's no maneuver which we're doing which would require high thrust. And so it's fine if it's just the very slow buildup of momentum over time.
So for a 100 kilometer circular orbit change from 400 to 500 kilometers, we'd need roughly 50 to 60 meters per second delta V. And with a 4 kilogram 3-unit CubeSat, that would mean 224 Newton seconds of total impulse. We aren't necessarily requiring this performance, but this is sort of a goal that maybe we'd like to achieve. And if we can, through finding higher efficiency, potentially exceed this goal as well.
Right. And so for power consumption, we said, well, if we're going to be drawing 6.5 watts in on the QuickSat, this will be 3 times the size. Let's say we can get 3 times the power. That gives us roughly 20 watts to work with. And then you'll still have like processing and radio and all that stuff taking up, let's say 10 watts. That should leave us 10 watts to spare from the thruster. And so that's kind of where that number came from. And then mass and volume is kind of a similar calculation. We have our 1U CubeSat. And so presumably when we move into the larger scale one, that 1U of material will still need to be there. In addition, we would like to add reaction wheels and other stuff. And so that means that we probably won't have more than a U to dedicate to a thruster system. And so we started by making ourselves just a very, very primitive cold gas thruster comprised of a paintball air tank leading to a valve with a SLA printed nozzle that we threaded into it. Just we first off kind of like see what an overall system might look like and maybe begin some classifications. And so with this thruster, we're able to get 0.41 newtons of thrust with a total impulse, or with an output of 5.5 MPa. There's more numbers. The net specific impulse was 26 seconds. And that's on the low end for cold gas thrusters, because this is not super optimized system. At the same time, it's not exactly clear how we might be able to improve that.
An important thing to note, though, is that we put out a proposal to a lab on campus to acquire a vacuum chamber. That has not been realized yet. And so this was tested at 1 bar ambient pressure. And our nozzle was not necessarily optimized. And so testing both at vacuum and with a more optimal nozzle would be likely to increase our efficiency. In addition, we had a very hard time finding very nice high pressure parts that are low weight and low size, or small volume. You can see that we use this fairly large paintball air tank and this valve here, which is really large. That's sort of an understatement. And so we if we were going to actually build a cold gas thruster that is going to go on a satellite, we need to find a source of nice low mass parts. And this is something that we haven't really been able to find, but if there are suggestions, we would love to take those.
Yeah, and so after we built ourselves a cold gas thruster, we were more able to evaluate it in terms of its potential mission effectiveness. And so we theoretically, a pure nitrogen cold gas thruster can get an ISP of like 78-ish seconds. Realistically, most of the ones that have been launched are more in the 50 to 60 seconds range. And so given that level, it take about 0.38 kilograms of fuel to get our desired delta V of 56 meters per second. And that doesn't account for fixed costs, including valve, including pressure chambers, and all of that stuff. And so it might weigh quite a bit. Additionally, we may need a relatively large volume for gas storage, and scaling up how much fuel we have is also difficult because you either get yourself a bigger pressure chamber, which takes up more space, again, more volume on the shell, or you increase the pressure, which again, you need more aluminum in order to contain it. And so scaling it is a non-trivial task. Finally, it may complicate launch because generally a lot of CubeSat launchers don't necessarily like launching high pressure vessels. And so we'd have to do some pretty extensive qualifications in order to actually get ourselves a flight.
So a technology that we'd like to look into for the future beyond a cold gas thruster is electrospray propulsion. So this is using an ionic liquid, a salt in solution really, as propellant, and then applying a high electric field across this ionic liquid, which strips the ions out of the liquid and accelerates them as exhaust. So this has been done sort of maybe most notably by a lab at MIT, the Sanchez lab, or sorry, the Lozano lab at MIT. This is an example of one of their thrusters. You can see the small size of it, which is really a bonus for this design. We also thought about the sort of problems we'd encounter in fabrication and use of this technology. One of those is potential evaporation of the liquid itself. But we have found that through some research that we've done, that this may not actually be a problem. This is a technology that for us is really, we're in the early stages of looking at. And we're potentially open to using other types of electric propulsion. But this seems to stand out as the best for us. So with this technology, an ISP of around 1,000 seconds is possible. So for that delta V of 56 meters per second that we talked about earlier, we would only need a small fraction of a kilogram of fuel, 0.023 kilograms. And it would be able to function with sort of a low power input, which is very helpful for our design requirements. On the other hand, it does have this relatively limited thrust, but for our purposes, that's not a huge issue. And then for all of this, we would need some power electronics that could step up our voltage really well. Would you like to?
Yeah, so we met with a professor here at Stanford University, Dr. Rivas, and what he was working on is essentially a little chip that could raise from 40 volts to 2,000 volts at 40 watts, and it could do this at just 3.5 grams. And so we think working with him, it would be feasible to get ourselves the type of potential difference required to operate an electrospray thruster without consuming significant resources on our system.
This image you're seeing here is a PCB with an inductor printed into the board. This inductor sort of has this shape, so it is a torus that doesn't produce really any external magnetic field, so it won't interfere with the rest of our electronics on the satellite, but it can have this produce this very high DC to DC voltage step up.
Yeah, so just to recap, there's positive and negative attributes for cold gas and electrospray, so the two things that we're considering. So basically, electrospray is good because it has the high ISB, but it's still relatively simple as far as electric propulsion goes. And that really contrasts against the very, very low ISP you get from a cold gas thruster. At the same time, it's very not simple compared to a cold gas thruster, and so it will take a lot of development to be able to make it actually work well.
So onto simulations for alongside.
So our goals for simulations are twofold. We have long-term and short-term goals. So long-term, we want to be able to build a full simulation testing suite that has adjustable modules that we can turn on physics modules or sensor modules based on what we're using for a given mission, and in-depth graphics development so we can actually see what's happening and visualize it. But in the short term, we're going to focus on just satellites, not SSI as a whole, and we want a functioning engine over developing the graphics. We're going to focus on the numbers first. And how we're doing that is we're using the entity component system architecture. So in usual object-oriented programming, you have classes and clearly defined systems. So for example, you have a class for like a planet, but in our case, we're going to have too many of those different components, well, planets and asteroids and things like that. So we're going to use the ECS architecture so we can just load all that in instead of using object-oriented programming. So we have two teams on simulations. The first is a physics team, which is working on developing all the systems for the architecture. So the systems are what update our frame to based on what's actually happening in space around it. So right now they're researching different engines that already exist to base our systems off of those, and then looking into what physics systems we actually want to implement. And they're also looking into sensor outputs. So if we have a given sensor, but output something in bits instead of like just an integer, so how we have to account for that as well in our development. And they're working in MATLAB. And then our engine team is more on the CS side of things instead of the physics side of things. And they're working in C++ to make our basic working engine, which they already have done. And now they're moving on to researching OpenGL and working on translating the MATLAB code that the physics people are working on into our actual C++ engine. So that is an overview of everything that we have talked about today. So introduction of the team, QuickSat, and our long-term project. And now we're going to move on to questions and suggestions. So I'll break it up by sub-team. We have
so we have these sort of sub-team name tags, if you will. So each of the sub-team leads and members of the sub-teams will take one of these. And for those attending who are able to sort of walk around, maybe give feedback, ask more questions, it would be great to do that now. All right, so I'll give the avionics one to Shai here. Structures to Connor. And thrusters to here as well. And then, yeah, I'll take it.
Why? Because like we don't have too many people. Why don't we just talk?
Yeah, I thought we were doing general.
Yeah. Oh yeah, let's do that.
Okay.
Okay. So if are there any questions or suggestions for us? I'm sure there are many, and I'm really excited for this, if possible. Yes.
Okay, so first question. Would you consider the ground link, the part transmitting the images down, would you consider that to be part of the fully operational system, or is that something that you intend to remove from any spacecraft that actually flies this, that actually uses this navigation method?
You're talking ground hardware?
No,
Right.
communicating the images to the ground and then doing the machine vision down on the ground. That sounds like what you're doing.
Yeah, that's definitely part of it.
Well, so the image classification we're actually planning to do on orbit on the satellite.
the image classification, the
Yes.
actual machine vision and backing out your location. Is that done on the
Would
ground?
also be done
That's
on
also on
the satellite.
That's on the
Yeah,
satellite.
the idea is having like a completely independent, self-contained kind of navigation on the CubeSat, so that if like ground stations don't work or GPS doesn't work, it's still a functional satellite.
Okay.
That was the idea.
Do you expect to be able to pack enough processing power into the satellite to do this on orbit?
That's something that we are looking into.
We talked to an assistant professor here in the Aeroastro department, who mentioned that he thought that using a Jetson for that to run a neural net on a CubeSat would work well. So then the avionics team talked about that, and I think Shai, you came to a different conclusion.
This is a really.
That's a technical term.
So we've had two people looking deeply into the processors. We had Julian Chandler actually has been who have a lot of experience.
Please don't make Chandler work on the Jetson again.
Yeah, so that's part of it. But it's just, it seems unnecessarily powerful for what we're doing. And it's just, like, it requires a lot of power as well. Like, both powerful with power, but also, like, with the rates we're trying to achieve. Yeah.
So the Jetson has flown in space and is space qualified. People put it in space and verify that it works. But to put more specifics on the Jetson being finicky as fuck, last year the robotics team, which I also did last year, used a Jetson as a central computer on our rover, and we need to recompile the kernel 8 times to get USB drivers to work. And the only reason we could do that is because we had 3 people on the team who worked at NVIDIA, and we couldn't figure it out, despite one of them actually working on the Jetson team. We need to bring over NVIDIA people to our lab to be like, and then they fixed it after like finicking with it for a couple hours. So,
yeah.
So it sounds like the answer is no. You're not expecting to do the machine vision and actual position determination on orbit at this early phase. It sounds like we're planning.
No, we want so that the goal is to do that on board, because with classification, it makes you have to do that on board, or else that's the point, right? Because you want to send down images that are interesting.
And that sort of plays into the price of downlink, that we only want to send down the images that are worthy of being sent to the ground.
Okay, but so why are you sending images to the ground at all? Is my question. If you're doing all the
So those are 2 kind of separate objectives. One is just normal CubeSat Earth imaging, so just get cool pictures.
So the classification is a technology demonstration of being able to classify images that you sort of would want to use and ones that you wouldn't want to use in terms of a ground downlink, and just sending the ones that you classify as being worthy of use.
And then the orbit determination is a separate project where we try to determine within this, like just from the satellite independently, where we are in space at any time.
Okay. If you are able to do that on orbit, if you're able to get your process, if you're able to get enough computational power on a CubeSat to do that kind of processing, what is the end-to-end precision that you would expect to get out of this imaging method?
How precise, like our orbit?
Yes.
We don't know yet.
Any order of magnitude?
I don't think.
So the way we'd go about it is by comparing images that we take with sort of a database of known features on the ground. And so if we're able to sort of get a model that can do that process really well, then I think you could get an arbitrarily good determination of your orbit just over time.
Well, you're going to have optics limits for one thing.
That's true. That's true.
You presumably can't know the position finer than the resolution of your object.
That's fair.
So
Yeah.
there's going to be that limit. But my concern is, even if this works, if everything works perfectly, even with a week-old GPS fix in low Earth orbit, you can still compute your present position with an SGD propagator or something like that.
That's a fair point.
To within a few kilometers,
Yeah.
10 kilometers at worst.
Yeah.
So if I would recommend doing an end-to-end tolerance stack up of every source of error in this system, assuming it's working perfectly, and determine what accuracy you'd expect to be able to back out your position.
Because it doesn't make sense to do it if it's beyond that.
Yes.
Okay.
Yes.
Okay. Thank you.
I have a couple other questions, but
Well, I guess, so I to build on that, I guess one of the thoughts, because it sounds like perhaps, I think knowing SSI and where it comes from, it sounds like perhaps it's more of a proof of the technology demonstration, like doing a bottom up approach of like where the air is going to stack up to. I think what might be helpful is to in fact set a design requirement for you guys of like, we know that we want to get within 10 kilometers, let's say, of position accuracy, because then at that point it starts to become a threshold of being
Like this
useful
makes
to replace
sense.
GPS and these sort of things.
Right.
to benchmark that, I would ask, how long, under what situation would you expect to be without GPS, and for how long? Because the only situation I can think of is a war.
Yeah. Yeah. I think so. That's a very fair point. I think for us, I mean, the rest of the team can correct me if I'm wrong, but for us, a large part of it is simply the like ability to do it a different way, which is exciting to us. But I'd say if any of you guys have more of an answer to that question, no.
So, so this is something that Dr. Manchester brought up as an interesting project
And
a quick
yeah.
kind of satellite. In the case of, let's say, G doesn't knocked out, or
in the very
something like
unlikely
that.
event.
So I guess one thing that we should just write down and do is just see more broadly what the applications of this would be.
The origins of this idea were that our sort of previous project idea was to take photos of asteroids in the asteroid belt and compare those to a database, a NASA database of asteroids, and use that to determine our position in space. And that would be used for, say, beyond Earth orbit navigation, deep space navigation. We found that in Earth orbit and sort of not near the asteroid belt, that sort of breaks down because of how dim asteroids are. Yeah.
Big primary to catch
Yeah.
asteroids.
And so this was sort of a sort of logical change from that, I'd say. But I think you're definitely right that having an alternative to GPS is maybe not, at this point, doesn't really seem to make sense. So we'll have to look into that, I think, a little bit more.
Maybe not in Earth orbit, but
Yeah.
I can give you an example where I would love this technology around Mars.
That,
Right
yeah.
now, precision navigation around Mars
Oh, there is
requires
nothing.
a two-way link with the deep space network. Without Earth, we have no way to do precision orbit determination for a Mars orbiter.
So I'd say that if we can demonstrate it around Earth, then it is potentially something that, with sort of a change of our database, could be applicable to Mars. So that's very helpful. Thank you.
The second use case I see there is presumably from this you could also extract your angular position relative to the Earth. So you could replace a star tracker system, and in a like future version, you could replace both a GPS and star tracker with like a single device. That always helps with swap. Like, I think for these sort of things, like there's always interesting ideas, like new technology. And this is sort of SSI and sort of things. Like, people will find new uses for that. I think like Dave's just motivated from a professor, and like it's a neat thought. I guess I wouldn't stress too much about like the exact application, knowing like we off the back of our heads we kind of come up with a couple use cases for this, and like I guess you guys aren't the ones that are going to send it to Mars, at least not in the time being. So like, I think it seems like it. I guess it seems like it holds validity, and like if you know that it holds validity, I would just encourage like, what are the use cases that you would want to design for, such that you have like a real functional
Like a capability.
that you can hit for.
Right.
So like 10 kilometers, for example, or another thing that might be useful even aside from GPS fix would be the attitude, so that you know basically like the reverse star tracker that
Mhm.
at the ground.
Right. Okay.
Um,
It is, I think, really good to know that, like, a possible use case though for this. So thank you.
I think that is a good idea though, and a preliminary deliverable of this, rather than trying to deliver orbital position purely from ground images. Try to get attitude. Try to do what your star tracker is doing first. That might be a little bit easier.
Okay.
That means one less camera, right? Depends on.
yeah, if you could replace it,
But potentially less hardware.
Sure. But assume you have GPS, do this, and then see if you can get attitude from that.
That's good. Thank you.
Follow-up question is, I guess, how related is this image classification? Like, know what we want to send down before we send it down, and then this like Earth tracker project. And is there like resource sharing between the two of them? Because in my mind, I can see for image classification why like neural net, lots of compute. I know nothing about that, but like sure, you need like really powerful stuff. Your thermal budget's gonna be whack. For something like doing essentially it's a star tracker problem with slightly different feature recognition layer, like that seems to me like maybe don't need to worry, like you don't necessarily need a neural network. If it speeds your development time, I think that makes a lot of sense. I think Raspberry Pi is a great choice of Python if you can. Like that's something that uniquely SSI can do, and like other people can't because they're like, oh no, permission. So like, run with that. That's awesome. But I guess an interesting question that I sort of have would be, what is the power trade-off for going for like a full neural network versus trying to do something like in C++, and which makes those easier to, how does that affect your development time? Like if you get something that, like I think basically because the tools are in place during doing a neural net to do a feature recognition and extract some kind of position data would be something relatively quick to develop, but might, like if you want to do a Raspberry Pi, I don't know if Raspberry Pi can accomplish that. Do you guys?
Yeah, so we're unsure if a neural network would be appropriate for the actual geolocation components of this. It would be a simple neural network to make to just simply classify things by like, this is clearly a desert or this is clearly a forest. That's a much more simple problem. Whereas geolocation, because neural networks seem to be best at things like classification, we're unsure if specific geographical features like being identified as like the specific place on the globe would be an appropriate problem for appropriate use of that. So we're looking into other potential CV methods.
And so for classification, neural nets are getting lower and lower power all the time, and so there are a lot of resources on running and it's on Raspberry Pi, so that's been done, and like you can do live kind of video segmentation. And
on Raspberry Pis.
On Raspberry Pi.
Okay, cool.
So,
then, yeah, totally.
And we don't need to have that frame rate if we're taking a few big, pictures of the Earth. So I don't think that would be a problem if we have that time. Depending on how quickly we want to take pictures, but even like it wouldn't make sense to take a bunch of pictures in the same spot because you're looking at the same thing. So I would expect that to be a lot of time to do that computation, and also there's a lot of work already done with TensorFlow on Raspberry Pi that we can kind of pull from.
I have a higher level question. Following on from Max's point, I think there is kind of an application for a GPS placement, especially on small satellites, because the chips can be kind of finicky and don't work pretty well, but whether you can get your system down below the size and power of a GPS chip, which is roughly the size of a postage stamp. So they've got it pretty small at this point. My bigger question is that you have two goals for the QuickSat project, which is build a satellite in 1 year and learn about all these components and do all of that. And these two goals might come into conflict. Mainly because you're 2 months through your 12-month design cycle, and this was a fantastic presentation, but it seems very much still at the conceptual level.
Yeah.
And as far as I could see, when you're building spacecraft, you have to trade every component. Do you build it yourself, or do you buy it in-house? It's a price versus time and performance trading. As far as I could see, you're planning on building everything in-house. And so what I would suggest is that maybe prioritize the components that you think are most important for your various goals, and maybe put in place a system of backups, just in case one team is running behind. So for example, if the Star Trek team is running behind, they get bogged down in midterms, for example, and they can't deliver on time, maybe have a backup one that you could just buy from an external company. And so focus on the geolocation stuff rather than potentially trying to build everything yourselves, which you might get bogged down in a Herculean effort.
Yeah, that's very important. Thank
That's
you.
also something that can apply to solar panels and stuff that's already been done before. That's not interesting.
The solar panels would be the first thing I would if you can build solar panels here, great, but I don't think that's really worth anything other than the bragging rights.
Every system of avionics, like we know what their like commercial alternatives. That's the first thing I looked into.
Yeah.
So maybe say we could do all this ourselves, and let's put teams on each of them, but let's have a backup just in case. We can't do it.
I'd like to build up that point, and specifically, I wasn't here for the radio presentation, but I've looked up on YouTube apparently somewhere.
Sorry.
And you mentioned using a high-powered radio. Would that be an off-the-shelf radio, or your SSI's downloaded radio design? Would that be?
David's working
Yeah,
on it.
something I want to work on.
Okay. I'm just thinking because, like, judging based on the pointer of communications are difficult.
Yeah.
It seems like a very single point of failure, and if radio doesn't work, then nothing else is going to. Like, we won't know it works. I almost feel like even having a commercial backup, even if you have a radio.
Because this is part of the like experiment is like a higher data rate radio. So this could you can have a backup TT&C radio and then have this as like part of the payload.
I was going to ask a similar question. So how many single string of failure do you have? If your geolocation thing doesn't work, do you have a backup GPS just in case? If you're
The GPS we use to validate that. So
if your high power radio doesn't work, do you have a backup TT&C radio that you can rely on? Basically, if you should assume that any or all the things that you do and make sure that none of those kills the whole mission. So if your solar panels don't deploy, you said you're planning on fail-safe, so make sure you can still do at least something in the spacecraft if you can't get those 6.5 degrees.
It's definitely something that CubeSats often fail like most of the time. So yeah, that's very important. Thank you.
It's more than 50%.
Yeah.
What's the CubeSat payload? It's a 1U CubeSat or?
But it's no longer a kilogram, right? You can go up to 1.6 now. 1.3.
1.3. Did
Sorry,
you?
so you're fitting all of that into one U? You're fitting deployable solar panels, a thruster, and new
No,
radios?
no,
So-
the thrusters on the long term. That's okay. Sorry, so thrusters.
So the deployable
what is it
solar.
that fits in the one U?
So the deployable solar panels would potentially go on the QuickSat. So we have the deployable solar panel, all of the structure, the long range radio, and then so the magnetorquers, if we put them in a PCB, that wouldn't be a huge issue. But if we have to take them outside of a PCB, that would also add volume.
It also depends on how quickly.
Yeah. Yeah.
Nice.
So for
So-
for a full list of what's going into the 1U, it'll be sort of the sensors you see here. Yeah, which will be a PCB. Magnetorquer, which also might be a PCB. And then the long range radio and solar panels. And these, of course, these optics will also be some volume.
Magnetorquer will be PCB, but in 3 axes. So that's also not.
Have the entire thing be PCB sandwich.
Yeah.
It's the sandwich cells.
You know,
That's a killer idea for our frame.
I have a question on the PCB spiral. You had mentioned in the presentation, but the magnetorquer rod is easier, like spinning your own coil is easier. Why is that easier than like ultimate?
Well, I mean, okay, the ultimate's easier, it's just a matter of like, it's kind of tedious to do all the spirals and.
That is very true.
Like, there's room for like potential fabrication errors, and like how many layers we're gonna do and how expensive does that make it versus just like having the a rod that's like, it's a physical thing, you spend it, like, if you can get it done like an hour. Like you can't get it done in an hour, it's a little binder, but like it's, once the wine is developed, which is in a pretty mature state right now, it become pretty easy.
Okay.
Try the in PCB spiraling. You can have a script automated. We did this for the other Manchester project. So we have a bunch of these in panel 4-layer boards.
Okay.
So I think four layers is enough.
I have a question on both of these.
I
Have
guess
you,
also for me, like it's also a little scary. So,
if you have that deployable array, you're going to have to point it at the sun in order to get full power. Have you done the analysis of whether these are strong enough to turn the satellite in the half an hour and 45 minutes ago?
I haven't done the analysis. We're starting looking at that math. We have like papers of equations, but we haven't actually worked out the numbers yet.
Because that might help you in the trade, depending on one is going to be stronger than the other. So,
Actually, I have a question about that. If you like Earth is here and then the sun is here, your magnetorquers don't need to constantly be going to face the sun. You can just put in an attitude which faces the sun, and you only have to adjust your attitude like on a year basis.
Yeah.
As the Earth travels around the sun, you have to do it.
But
Only if you're in sun sync. If you're not in sun sync, your orbit is going to recess after about a week.
also, you're going to have to point the camera, and so you're going to have to think about pointing the panels, the camera, and that's going to change. And so that might be more complicated than it sounds.
It's possible that the structures team could look into actually actuating the solar panels. That's probably a horrible idea, but
Where are your batteries?
that's a fair point.
We want to figure that out to figure out the solar panel doesn't really know right now. Has avionics talked about batteries? Not really.
I think so. We had some mention of, I guess the difference between maybe using like different energy densities, like using a lithium-ion battery versus like a LiPo or such. But that is, I think, something that we have definitely like not fully. Yeah, we've definitely missed on that one so far. Yeah.
Well, have you thought about what you're going to do in darkness? Because are you basically going to shut the satellite down for half an hour? Because there's not a whole lot you can do. If
That's a fair point.
Actually, what I wanted to ask, would it be easier on the night side to do this geolocation? To use geolocation by looking at urban outlines, because those are extremely predictable.
Oh, that's also true.
They're just
That's
gonna be
really
just obscured
smart.
by clouds, but they don't change
Natalie,
color.
are you taking notes?
You don't need
thank you.
multiple band passes. Just it's urban star trackers.
That would be ideal.
But you have to operate on the night side,
Yeah.
which means batteries.
You need a lot of batteries.
Yeah.
that also means it would not be a valid thing that we could use on Mars in the short term.
I will make that.
So pick one. Pick one project that you think you can manage and stick to it.
Yeah, that's
At least on Mars and then March.
The new SSI.
yeah. Thank you for highlighting that.
I mean, we definitely thought about that. It's just not something maybe I could have gotten around to.
That's maybe something that we should think about in terms of like a systems kind of.
Do you have a whole system overview, like somewhere there's a big CAD model with different spots allocated for each subsystem? Or are we still at the concept stage?
So that's something that we've been talking about doing in our systems team, but yeah, the answer is no. Yeah. Yeah, it's definitely in the concept stage there. Yeah. At this point, we're really sort of developing, like going intensely into the subsystems more so.
We also want to make sure that our missions actually make sense. That's one of the reasons we invited you is to do like see whether or not it even makes sense to pursue these before starting to really build it out. And in the meantime, the subsystems are kind of looking for
The technologies that we've developed or that we've been working on so far could be used for many different types of missions. So that's why we wanted to have this now, is to sort of hash out exactly what we're saying. Yes.
So I have some questions. The first one is about attitude determination. Do you know like how the math works out with like the competing interests of like facing the sun versus like staring at the earth for the to get your attitude determination working?
In terms of like power capability, or
in terms of like, I'm not good at geometry, but like can you do both at the same time? Like both point the solar panels at the sun and point the camera at the earth?
No. I mean, it depends on where you are in orbit. Like if you just happen to be like.
Yeah, not always.
Then, or how your panels are laid out, but no.
Will like, how does attitude determination work if the like camera is not currently pointing at the earth?
So you mean the like orbit determination? So there's two things. So one is attitude, which is just saying where are we pointing in space.
Yeah, how does that work?
So that's the star tracker. So we would look at the stars, and depending on where their camera's on the CubeSat, what stars they see, we know where it's pointing.
Well, or under Max's suggestion, that would be the sort of an early stage.
Or the other way where we look at Earth and depending on how things are being skewed, we can determine where it's
Yeah, my overall point is that like there might be considerations based on like you have to like point at the sun and then maybe lose like control or like lose accuracy on your attitude.
Yeah, that's definitely something that I think batteries would be helpful for. But yeah, that's a good. Yeah. Yeah, that's
typically 20-25% of a CubeSat's mass.
right. Yeah,
In volume, they take up a lot of space.
that's true.
My next question is regarding the satellite image datasets. In the data that you have access to, like how many different cameras are being used, or like how many different like orbitals are they going over?
We're using one specific data set, so it's just like the same.
Which is possibly problematic for us, but we, I think, looked into multiple data. I think Katie knows more than I
There's
do.
lots. So this one like website has a ton of data sets, so we have to just pull different ones. The images are just formatted differently, so I'll have to account for that.
Just to clarify, you have two image sensors, one for looking down at the Earth, the other for looking at stars, correct? There's not a. So two total.
Yes.
Well,
If we go with the star tracker or
The star tracker and then the pictures that we're trying to filter
And the Earth-oriented one is only one image sensor.
Like, we could do more.
Okay.
That's been my assumption.
Mass.
Those have been very helpful questions and suggestions. If you,
I think the biggest takeaway is what you said. Because if you can, this was pitched as, assume we have a star tracker. Let's see if we can operate without GPS.
Uh-huh.
Turn that around. Assume we don't have a star tracker. Assume you have a GPS.
but not a
Try to find a way to operate without a star tracker.
right.
By doing feature recognition on the ground. That to me sounds like a easier problem, and a problem with a more pressing need of a solution, because GPS antenna are tiny and getting smaller. Star trackers, not so much.
Uh-huh.
So that strikes me as the most important takeaway. Consider doing that.
What you could also do is, as well as a star tracker, think about an Earth limb sensor. So a sensor that tries to find where the horizon is and use that to also help you determine what you're pointing.
Oh, that's great.
So seeing where we are and then where the horizon is will give us like.
Yeah, so as well as using stars to figure out where you're pointing, use where the horizon is and where the sun is. Actually, three separate things: star tracker, sun tracker, horizon sensor. Some of those might be easier problems than others.
Yeah, all three of those will be bad.
Yes. So for
Not location.
Yeah.
So you'll need something else, but don't just think about star trackers. Maybe think about other different systems.
Right. All right.
We have been looking into some some training as well. It's just it seemed to be deprioritized, so we had presented. But if it's valuable, we definitely already have a lot of thought and research gone into it.
I think you're talking about something. Are you talking about
Like moderate is like this one.
Yeah. I read a few papers about instead of doing star tracking, just like where the sun is, and that's kind of all you need. And so that would just use the same kind of a camera, with different specs. They just accept the sun.
I like to imagine that if your star tracker is accidentally pointing at the sun, it doesn't work. So that you might also have to think about that. Figure out where the points are.
Let's do the pros. Happened last week.
Yeah. On
On the Israeli probe.
oh really?
They pointed their star tracker at the sun.
No.
That's it. The mission's not over yet, but they missed their first two orbit raising windows at perigee because the star tracker was right.
Oh, but so can they not determine their attitude anymore?
They have alternate means. So the mission's not out yet, but it's still in.
Wow.
Is this the lander?
Yeah.
Interesting. All right. If there's nothing else.
I have.
Okay. You go.
Sorry.
Okay.
So-
yeah. Thanks so much.
Somebody said that the Raspberry Pi needed 5 watts to operate.
It's like,
They had this conversation like an hour ago. That's like
The absolute theoretical maximum is like it might theoretically maybe somehow reach 5 watts, and we just want to make sure there's absolutely no reason that our Raspberry Pi could ever be bottlenecked by power.
That's what I wanted to check. So you said that if the computer needs 5 watts and your deployable array gives you 6.5 watts, then you can't do without the deployable array. So that now becomes a mission critical thing. So you should plan to at least have a low power mode as a backup.
Yeah, and like the Raspberry Pi would be able to run at lower powers. It's just like the goal of the deployable solar panel is that you can have absolutely no power constraints in terms of what your Raspberry Pi can do.
Remember that you don't have explicit control over your Raspberry Pi's power consumption. So if you don't find a way to cap that, you can get stuck in a power cycle.
You actually
Pulls 5 watts, can't get it, shuts down. Pulls 5 watts, can't get it, shuts down.
Right.
And there's no way for you to break it out of that. So
That's good to know.
you actually do have control. You have custom control over the processor clock speed, so you can underclock it quite a bit and force it
that's
to
correct.
run at a lower power. My other concern with Raspberry Pi is I know there's various different models of Raspberry Pi, but they all operate off an external storage device, like as an SD card. And I think the idea of, we're concerned of putting an SD card in the Raspberry Pi on a rover which kind of drives around campus with those vibrations. I'm not sure how SD cards will like, space launch. And I've looked around and there isn't any good alternatives for offloading that to other systems. So I'm not sure what's your plan to solve that, or just add reliability. I think it's a very micro issue, but it's something we're thinking about.
There are definitely ways that we can collect USB.
I think micro SD cards are fine with the vibration, radiation less so, but yeah, we launch them. We launch the station.
Slotted in there.
It's in one of those metal capture tabs. You put it in a metal piece on top of it. They're not exposed payloads. They're inside the station, so different radiation and thermal environment. But mechanically, I think they're okay.
This isn't gonna be the first time like a Raspberry Pi has been launched. It's like pretty common.
Okay.
I had some question about the communication subsystem.
Yeah.
So you'll have to think about one radio versus two radios,
Yeah.
build versus buy, etc. Have you thought about the other end? So what's your
The ground
ground
station.
system looking like? Because
Um,
you mentioned different frequency bands using S-band or UHF, VHF.
Yeah.
Have you thought about, are you talking to a place at Stanford? Are you talking to
the roof antenna here is a 435 VHF, and that's what other missions have been using. But there's kind of and then in addition to that, there's the radio club on the hill.
Yeah.
Not the big dish, but they have some other.
Yeah, they have.
So we've been using their resources as well. So that's just kind of like easy access, what we have here, not having to like go rent time on other ground stations.
Absolutely. Just something for you to consider that might inform your trade on which frequency band to use.
Yeah. Rent some hours on the big dish.
I would. I don't think it can track that fast, but you never know.
Are there?
Look at what PhoneSat did.
Okay.
They did a really good job of getting a powerful big antenna in a tight form factor by just a tape measure, wasn't it?
It was basically.
Just a tape measure.
Was it just a tape dipole, or was it something?
Yeah, so different CubeSats have different.
100% volumetric packing factor.
That's amazing.
What you can do is like string large things off your satellite, or you have what they call a turnstile, where it's 4 different things that pop out.
Okay.
Some people put the antennas on the solar arrays, but you guys might not have arrays, so that's one way of doing it. Or you have patch antenna, different things.
Okay.
But ideally, you want to make sure that you can get a link with your satellite, regardless of where it's pointing.
Something isotropic.
Yeah. But the length of the antennas will depend on your frequency band.
Are there any other? I do have a question that I asked partway through that I don't really expect an answer to, but for the cold gas thruster, we had a very hard time finding small, lightweight components. Does anyone know, like, about any sort of source of components like that?
Sure, they'd be the best one to talk to. If you, for when you are ready to incorporate propulsion, though, I would strongly recommend low thrust, high SP, not a cold gas one.
Okay.
Because cold gas engines, you're pretty much going to have to put in an RCS into the system.
Right.
Because
you end up tumbling.
They are high thrust and they are going to induce a small tumble.
Okay.
Lower thrust systems, like if you have a grid, it can be its own RCS. That is much more difficult to do with cold gas thrusters.
Right.
Because cold gas thrusters are going to induce a tumble. So when you're ready for propulsion, I would strongly recommend going with one of your low thrust options.
Right. Okay. Thank you.
I was going to ask on the Electrospray thrusters. You said like the using those little cubes was far more complex. Assuming I think like the operating physics behind that is guess if you have to like build your own like ion wells, then
Yeah.
But if you're getting like, it looked like that was some kind of a product or a research team.
Yeah.
And like, if you had that MIT lab said, hey, here's a cube, is that actually hard to use if you have the cube?
I don't think so.
Okay.
Yeah,
because then, like, don't mess with the pressure vessel. Like,
Yeah.
all you need to do is give it a little bit of a power supply, and you don't have to worry.
Yeah, the hard part for us would definitely be building in-house.
Were you planning to build that or what?
We were planning to build that. That is sort of the reason why that the long-term project is a long-term project, because that's a hard
What
thing.
equipment would you need to build one of those? Like, is it like an SNF kind of a thing? Like, do you need a nano fan?
So we are honestly not sure if there is a design of an electrospray thruster that doesn't require those sort of like nanoscale nozzles that you saw in that photo. We hope it's not, but if so, then you're right. Yes, we would.
I have two thoughts. One, I know Juan Rivas was working on an ion thruster to show off his high power converters.
Yeah.
Was that an electrospray or is this a different thing?
So
is he not actively building one of these?
So he was working with Professor Mark Capelli in the mechanical engineering department on that. We were planning to set up a meeting with Mark Capelli. I don't think it was an electrospray thruster. I believe it was a Hall. It was either a Hall effect thruster or some other type of plasma thruster. Yeah.
Because I guess in both of those cases, whether you can go to Juan Rivas or you found the folks at MIT, like,
yeah,
you know,
we could definitely reach out to them, and yeah.
You have a unique. I would guess don't sell yourself short, is you have a unique opportunity to a lot of those other labs because you probably have a better chance of getting launched, similar to the Pointer mission. Odyssey, like y'all have connections, so as an academic, partnering with you might actually make a lot of sense for like a way for me to get my crazy electron spray thruster in space, and like otherwise it's gonna take 5 years. I'm never gonna see it.
Right.
It's never actually gonna go there, and I'm gonna have to graduate, get my PhD, and go out in the world before it's ever needs.
Right. Okay.
So like for you, like I don't know the specifics, but whether it's the Juan Rivas Hall effect or like just like that lab there that you show that picture, call them and say, hey, we're doing this mission, launching in a year.
Yes. I'm also aware of at least 2 startups building electrospray thrusters.
Oh, really?
So
okay.
They do exist.
Yeah.
And you might just be able to call them and say, hey, we can demonstrate this for you, it'll give you some publicity in return for a free thruster.
Okay. I'll have to ask you about the names of we did actually in doing research we found places that we could buy them online, but also I think reaching out to the MIT researchers or those companies would be great. Yeah, thank you so much. That's good to know.
Knock the fact that you get like the opportunity you guys have. Know what you're uniquely good at. I guess, and that's one of them.
Okay. Thank you.
Axion Systems is the size of electrospray, or is that something else?
I don't know what Axion is. I thought it was. I don't know the differences between them.
That's just all like Western Axion Systems. That is yeah, that is Axion Systems. That was just fantastic.
I didn't know the name, so I didn't know.
Is there?
So what are your next steps after this review?
So it varies by team, but we did sort of. We'd like to be at a point where we can apply for a launch through the NASA CSLI or Alano program this summer. And so that would mean sort of a full up design in a sense. I mean, I could definitely speak for the thruster team in terms of like what we plan on doing during spring quarter. Like we'll be looking into the electric propulsion. Definitely
For the
reaching
long
out.
term thing?
Yeah, for the long term, because the thruster project is not really going into the short term project.
Oh, I see.
We're going to continue working on
But
that.
in terms of the QuickSat project,
Yeah.
where you're planning on handing it over in December, what's the next big thing?
So,
I think so.
The first thing, and that's kind of this is part of it, is finalizing our mission, getting that completely solid now. So we know exactly what we're going towards. And then on a systems level, basically specking out what we need to then accomplish that, what bag of like power that we need. So that's the battery, how things are going to start to package in. So we're starting to get mass budgets for different subsystems, all that. So that's on the systems level, and then on the individual subsystem, they'll have their space to work with, and they'll we'll all be doing what we discussed. Short term is mission, kind of finalizing that, and then the systems level, puzzle kind of starting to put it together.
Do you have a systems engineer, or is that currently being handled by the team leads?
We have a systems engineering team that is composed
It's
of
just the leads of the sub teams.
Yeah, it's mostly the leads and stuff.
So who's in charge of this? Like, is there one person who is responsible for delivering this? It's kind of a committee.
That's mostly Katie and I. So as the co-leads of the satellites team, we're responsible for delivering this. At the same time, because of the nature of like the structure of this club, we sort of are only in our roles for a year, and so it definitely doesn't have that sort of like we have one project manager who like is like on the hook for like making sure this is done, which is of course a problem of the structure, but yeah.
But you can't really do much about that.
Yeah.
As students, right?
Yeah.
So what I would suggest is you pick one person who at least until September is responsible for this. And then the first thing you do is you set out your system requirements. You say these are the requirements for the mission.
Mm-hmm.
Then you have a review kind of like this where you say it has to be 1 U volume, 1.3 kilogram mass. It has to be able to define not only position but orbit determination, which means several different positions down to within 10 kilometers. Needs to broadcast down to the ground station somewhere on the Stanford campus, which restricts you there. Needs to be able to launch through NASA, maybe they have their requirements. You need to be able to get a license for it, which restricts your frequency bands, etc. And then teams go off and design and say, okay, we have this envelope, this is what we have to work with, and then the teams can go and design. So the battery team has 0.3 U's to work with. The Star Tracker team has 1.5 centimeters to work with them in the stack, etc.
Mm-hmm.
And then whoever's in charge, you own that, the whole overall design.
That's very smart. Thank you. That's very helpful. Thank you. We'll do that. Yeah.
You both do.
Yeah, that's
Other teams.
Systems engineering is Excel engineering.
yeah.
So what we can do, so our next system meeting Wednesday, we can look at that and say, like,
Yeah.
who wants to be the person to blame for everything. Basically, like that. That's what it is.
And then and the person who gets stuff to happen. I do think this top down approach is very if that's sort of what you'd call it. Is very helpful.
Yes. What you described and what this we do is it's more bottom
Bottom
up,
up.
top down.
Okay.
You
I
have
see.
you accept performance metrics from your sub teams.
Uh-huh.
Every piece of the avionics reports upward how much power they're using. Every piece of structures, or someone on the structures team polls everyone else on every other team for mass and location of CG for every component, and then reports upward. And it gets synthesized all into one top level design sheet where you can track mass budget, power budget, the CG location, the combined orbit and irradiance and solar power availability. You all start tracking that in one common location. It's dangerous if you start doing that too early, but
You have to do it at some point.
you do have to do it at some point.
Okay. Thank you.
I have a general question. We'll have to be picking a orbit we want to go in.
You might not get to decide that. That might depend on your launch. And I don't know how you're planning on getting the launch, but you might have to take whatever you can get, in which case that would inform the design.
Right.
So if you're in a sun-sync orbit, you might have different pointing requirements than if you're in an equatorial orbit. Something like that.
Based on what you're doing though, if you do have a choice, I do think SunSync is going to be your easiest one. Minimum battery mass, constant lighting conditions for your image recognition. If you do get a choice, SunSync seems like the reason.
Okay. Interesting.
But the height of that could change. So depending on the height of the orbit, you're going to have different lengths of time and night and day. So that will also drive your design. So if you can find out the launch ahead of time, or you assume a launch as a baseline, you'll have to design towards that.
Okay. All right.
One last thing we wanted to ask about was for our long-sat mission. We don't exactly have a mission yet. We know we want to have a thruster and a long-range radio and things like that. But any suggestions of like some interesting things to pursue?
So the most common thing you use a thruster for, at least the kind you were talking about here on the CubeSat, is mission extension. So if you want to extend your CubeSat's life from a year to 3 years or 5 years, boosting it up to 500 kilometers is a good way to do that. But typically that means you're going to have to design all your other components to last that long, which may be a challenge. So if not mission extension, end of life retirement. But that's also not terribly necessary in low Earth orbit. It'll happen anyway.
You can demonstrate an end-of-life deorbit, which is what you suggested, right?
Yeah, except it'd only be a demonstration. It wouldn't be necessary.
Yeah.
400 to 500 kilometers, you're coming down in 3 to 5 years anyway. Well, maybe not this solar cycle though. This says NOAA is predicting an extremely delayed onset to the next solar cycle. There's virtually no solar activity right now, and there's probably not going to be for another 3 to 5 years. So atmosphere is nice and cold and tight. Nothing's deorbiting.
Interesting. Wow.
What I would do is just, you have to, again, the same QuickSat, you have to define the requirements of the mission. So think about, even if you don't have a specific purpose, you have to give the sub-team something to work towards. So say it's going to be 3U CubeSat. It's going to go into low Earth orbit versus GEO, or we have to launch it within this time frame. It's going to have electric propulsion on board, and you get 1U out of 3 is propulsion, and then the propulsion team can go away and say, we want to do cold gas, or we want to do Electrospray or something. And so you have to give them some parameters to work with it.
I was going to say to that, I think what it appears to me now is that you guys are kind of as far as you can get without actually attaching numbers to things.
Mm-hmm.
And now that you need to start attaching numbers to things, you're kind of running into this thing where it's like, well, I don't know what my, like how much magnetic torque I need in my magnet torquers because I don't know how quickly I need to detumble because I don't know the batteries. They're like, you all need to start here, like starting to intersect with each other, and like there comes a point when you kind of just need to define some numbers. I think that what you might find, I know there's like kind of in SSI traditionally they push back against that. Like we'll start from what our like components can do, and then we'll like get eventually to something in the middle. But I think that you'll find if you actually define a couple of key numbers for each subsystem, that you'll actually find it tremendously freeing, because now suddenly you'll be able to actually make design decisions and move forward with a lot of the technical work here. Because what I see is a lot of a lot of ideas and a lot of concepts, but there aren't numbers on anything yet. Like there's no numbers for like what your required B field is on the these sort of things. And I think externally that's a little bit troubling. But for you guys, you can decide like what you need in order to decide what's going to work. And I think I would really recommend just attaching some numbers to things, because I think you're at the point now where the system and this system, you need to make calls, but you can't. There's not enough decision-making power among any one group, so they all have to build something that can interface with an arbitrary version of the other person. And like that's not.
Yeah. Oh, sorry. Yeah, go ahead.
I was just going to say that one of my company's mottos is that engineering is done with numbers. Everything else is just an opinion. And so, unless there's, as you say, there are no numbers on there at all. There's some measurements. But yes,
Magnet workers particularly is in an early stages. Trying to get.
I'm not sure you can design a satellite by committee. I think you need a program lead, program manager to drive things.
Right. Yeah. So would you say that for like critical numbers or for any number that we could really use, that sort of making an early estimate of that and saying like that is what we're shooting for, and then sort of building everything else off of that, and then maybe re-revising later? Is that what you're sort of
nailing your feet to the floor as much as possible right now? Because right now you have like nothing.
Yeah.
So like any decision you make is probably a good one because you made a decision.
Okay.
So like just I would say you have a lot of, you guys have been sort of stewing this for 2 months now. It sounds like you have a lot of ideas about what is probably mostly correct.
Yeah.
And I think that you should make a call now, because the only way to figure out if that's wrong is to actually progress down a bit of a design path. But that requires engineering and math.
I would suggest you need a baseline. And the baseline for all of these can change, and then you email everyone about it, but you need to have a plan. The plan can change, but you need some plan to follow.
Okay.
It's like I want to say.
That's which is why I say it.
It's like I feel like the most practical way of going about this should be okay, each team, you know what components you need, right? Like structures needs a frame, maybe Onyx needs magnet torque, battery, yada yada yada, right? So you're okay, all your sub teams here, you know what you need. Spit back to us of roughly what you think you'll need, and then the systems person can look over that, or should the systems person kind of arbitrarily decide things without first asking the sub teams what they think they want?
The systems person should make those decisions, but only after synthesizing everything from all the teams. There's no reason to don't tell the avionics team, no, you're consuming too much power, until you have taken a power budget for the entire spacecraft. Once you have all that information from all the teams, then you can start telling people if they're violating constraints.
Yeah, and I think that's the second step in what should happen. The first step is to define the requirements for the mission and have a sheet of we want the mission to be able to do this, 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 and this. And those can change over time. If the 10-kilometer requirement becomes too onerous and it's going to take too much power or whatever, then relax that. But you need to start from a concrete set of requirements with numbers.
So my understanding of the process, get these specific, here's what we want to do. And those down to the sub-teams. Sub-teams will look over them and say, okay, here's what I think I need in order to get this mission done. And then the systems person will kind of synthesize that and distribute mass budgets, power budgets, yada, yada, yada to the teams. Is that a roughly?
That's one way of doing it, yeah. And it might be that the requirements change once what you need comes back and it turns out that the requirements are too strict, or maybe we have some excess margin. But yeah, that seems a good way.
I have two thoughts real quick. Sorry, but what was your name again?
Damien.
Damien?
Yeah.
I thought you did a great job. Your slide had numbers. If you want an example of a version of this where they're I think you did a good job of isolating yourself from perhaps some of the noise of everything else and saying, hey, okay, I need 5 watts. I'm going to use these 2 bands. When I look at the different projects here, I think that yours was the one that just to highlight that for a moment. I think you did a good job of saying like, all right, like I'm gonna figure out what it is that I need to accomplish and get some hard specs on that, which is tremendously valuable and something that I think would be beneficial to the other teams. And maybe like, I know SSI is like a bit of a different, it's a bit of a weird beast, and so like it's hard to maybe like get everything up together and then go back down and like to build like a master systems document. I think as much as possible that should be done. But if you're like just to stop the bleeding, like do what Damien did, I think is maybe what I would, because I think that was a good, at least a step in the right direction. And I'd like to highlight that because I think you did a good job. Thanks. And then the last thought is I think that there's sort of like a severe lack of why right now. Like you mentioned, like we could do gallium solar panels, we could just use silicon solar panels. It's like why? I guess there's like an interesting technical like gallium's neat, but like aside from that,
It's primarily the efficiency, because twice as efficient to gallium, but it's also like I don't know how to go about it. So sort of like, I can figure out a good way to go about it. It just for efficiencies, we can have more power outage output. Because as you said, we don't really have firm numbers on all the power systems. So just trying to maximize it as much as possible. But it's trying to go over.
I've been talking for a long time, so it's your turn. Sorry.
I could be wrong about gallium arsenide panels, but I think they are only more efficient significantly at the beginning of their life. I think they decay on orbit much more rapidly. So expect your solar arrays for end of life efficiency, not beginning of life efficiency.
That's really good to know.
So ours.
But we don't worry about that.
Don't eat the panels.
One of the other outputs that when you give the requirements to the sub-teams, they'll come back, I need this much power, I need this much mass, I need this much time, or I need this many people. And then the project lead should think, is this within range? Do we have the people resources to do this?
That's very good.
Whoever is going to do that when we're done here, we have an example of a spacecraft level design sheet.
Is there anything else? All right. Thank you. Thank you so much for coming, for taking your Sunday afternoon to be here with us. And those suggestions were incredible for because we honestly would not really know where to go in a sense that we do now that you've been here. So thank you.
Thank you all for presenting. The opportunity to throw rocks at you.
All right. Awesome. Oh yeah, we should check out this. Yeah.
Because wait, so are you just using my design?
It looked like it did.
Well, I didn't.
It didn't have its back, so.
Yeah, well, it's interesting.
Memorize visual photograph.
Okay.
So
we're in the middle of
so for example, I have one here that has all the properties of the
Oh, wait, I would be super helpful.
I was kind of waiting for something.
It's turn.
Oh, yeah.
Sunlight availability.
Yeah.
The eclipse duration.
Laser array.
That is taken into the solar array.
Turns out the contractor got it.
Solar array sheet doesn't. All of that.
Yeah.
So you have 4 employees.
Yeah, 4 people.
Has a mass that they can attract.
That's
the beginning. Same thing about thermal control. Same thing about radio.
Pretty good. Basically, like
every subsystem represented.
Yeah.
And where they can talk to other systems.
I was talking to
Mass, their power.
one thing.
Like that.
Like you
There was
you
another sheet where
you might need the extra efficiency.
Here goes.
I find this a very useful way to see multiple teams praise of each other's work and as a way of making sure that everybody's probably the spacecraft is 500 transits. You're consuming 10 watts of power. And you're gonna have to start carrying that dense. So you can't just tell all the teams same power power savings. Same thing with mass. Probably gonna be this is how you track. This is how you track top level.
I tell you, dragons raised up your
So that's what I mean. I'm sure you already have spreadsheets that you can kind of put it all together. Your assumptions get tracked.
There's a chance to be one dragon return. There's gonna be another window.
You actually do get a little bit more.
They get out and come back and say, no, it's like actually impossible.
And you can also
I
like
trying
to get
we had a
that's
for that short deadline, you'll sit there.
it's not the first thing you should do because then you're going to get locked into your design. You don't just you're not going to want to change the design because it's going to change the structure. That's bad engineering.
There was
Once you have your mission requirements defined, and you want to start tracking numbers.
Double check.
I don't think, yeah, I don't know, like, I don't think that's a good way to do it. But I also think maybe that's.
It's like half the reason that there's a lot of ways to skip the last one is because they just don't want to machine it. It's like, hey,
Thanks so much for
curve cut it, decrease something like that.
It's see.
Just on our slide, as a journal, is that
I don't,
That was just sort of.
I don't think that's a.
He recommended something.
Yes.
So he's like, yeah, so he was trying to, I guess, that was not, no, that's. So he's trying to talk about.
Yes, the contract for the recycler was up for competition 3 years ago, and that's decided to go.
I was talking to
We already have two versions of there.
That's true, but it's.
So you're not sure last quarter.
I know.
All printers are still thinking that we probably have to as our
But
probably
I
our
think
fiber optic
that-
manufacturing side.
This, other presentation.
He said he did some yeah, it's the first stuff we're gonna be making that's supposed to be sold in space, but really what we're working on now is
I know you
what
guys.
they call Argonaut.
Like,
It's spacecraft that'll
Space
construct outside stations.
But.
What do you want on specific?
you mean apps?
Policy.
That's basically like.
Honestly, I'm sorry.
So-
Sorry if I heard politics for some
I know it's a little bit further. But I think.
We're still trying to work on a relay.
I was trying to.
So I heard about the sort of like trying to figure out what.
I know, yeah.
I didn't really expect any people.
Hey, yeah,
Because they're on some public.
yeah, it'll take more. You guys have the background now, it'll take a week.
Definitely not cat, it'll say tens of something.
Really, full of very specific.
The structure that we're in class right now. That is
So what's
what
that?
I think would be.
classes get.
All our stuff is public.
Oh, yeah, Zach told us about that.
I'm really excited, cause like, I have.
Go check out my video.
It's just that
Yeah.
it's overwhelmed, and I don't know if it's
You went.
But so,
Yeah.
like, a lot of it's just trying to make it easy.
So I would just say like that's a great example. Like, put that in there, you know, that like.
Like our team,
it's all- it's all
like,
opinion. So I did it for a report.
For a few courses.
Yeah, the
It's all
background.
dedicated, like.
Rails that's sliding against.
But it's good to see.
That's
Your classes, like, the first days, you
I would
get.
love to see them that. Presentation.
Thanks so much. Thanks
Yeah,
so much for
for
coming.
example.
Good luck on the progress.
I think just to see like that amount of time.
Work guys, I'm sure if you need more advice, you know where to find me.
Yeah, thanks so much. Yeah.
Thanks.
There's a pretty serious
I like it.
wage and volume sacrifices taken from the mechanical side in order to just make it easier to machine. So, if you guys are trying to do this as like a more
like try to pull under 100 grams, and yeah, you're gonna need to do
Everybody is designing an arbitrary version of the person, and that's not
but
the case.
other than that, yeah, you're trying to do a lot of stuff as well. So either just pick what you really want.
Yeah. The batteries was that
Well, so yeah, you definitely want to look at the volume range for batteries alone.
Care about the board.
Yeah, so the
Yeah, if everyone, great job.
Thanks for coming.
thanks for yeah. Heard it was. Yeah, I'm just coming off of that.
Hey, Connor.
You and Arlene were over that.
So, Doctor, so you guys mentioned you're using the classes structure.
Yeah.
Okay, so I'm the one doing that right now. Class.
My name is James.
So I just wanted, so you do need to hard analyze the minerals.
Yeah.
That is like a requirement from the tech guys. Like,
I used to be.
these are all the things that you're
Around here,
must have like 2 deployment switches and 1 rail switch running to the frame. You have to have like hard anodized, right, all the surfaces contacting the rails. You need to like use spring loaded
That's cool. What's your area of
push away.
cool.
Also, so yeah, I was using CC1.
I guess that's
So it's like that area, but I'm like.
So, 7075, is that driven by analysis or is that just like?
I was a master's student.
Yeah, since most of the stuff, like we're getting off the shelf brackets and stuff like that.
I thought you
One
did a good job.
design you want to look at also. Do you guys have to see the switch class for your own?
That's good.
What are you guys planning?
It's possible to access to a CNC. I wouldn't say we can have like, it's not crazy. It'll be nice.
Would be about.
No, also, yeah, we may have $2,000 of budget.
That's also, we also have a budget, so.
Oh, yeah.
It's not-
I would look through that.
How long you
Way that they use it, it's pretty good. So they have 2 plates, and they CNC and
Yes.
CNC the rails are and
Have
then
you-
they just
have
have
you studied any more?
plates.
Yeah.
And that's the entire.
Like before and then.
But the things go side by side.
Yeah, it's side by side.
Oh, that's
So
pretty
there are 2 plates.
They're like,
there,
Philip,
and
you
those
said
plates act-
you said like 10 weeks, like.
Yeah, come on.
Okay, you're like, slow down, but yeah.
That's pretty cool.
For the vibe, it's not that bad, or at least you need to do modal analysis to check where you stand with that.